So far we have looked into concrete without any admixtures. We have just looked into basic concrete with cement, water, fine aggregate, that is usually the sand, and coarse aggregate. But modern concrete cannot be thought of anything without a kind of admixtures, particularly the one which modifies the workability or consistency of concrete. Also we have mineral admixtures which I have mentioned earlier. So, they have some role as far as improving the workability of concrete is concerned, some of them. So, in this module 5 lecture 3 we will look into fresh concrete and the role of various admixtures. So, obviously as I just mentioned, our discussion will be first on chemical admixtures, and this includes what are called water reducing agents by and large. Today we will discuss only on, mainly we will discuss on water reducing agents. There are other kind of chemical admixtures, they do modify the properties of concrete, and we will define what admixtures are. Then in this water reducing agents there are 3 varieties: plasticizers, superplasticizers and hyperplasticizers. Okay, we will discuss about them all, and then we will talk about mineral admixtures, mainly fly ash, which has a strong influence onto the workability of concrete. Right. Let us define first admixtures. Since we have started with the admixtures, we have defined, let us define the admixtures. Admixtures are chemicals, okay. They could be minerals as well, as we are calling of mineral admixtures. They are added to mortar or grout at the time of mixing to modify properties either in the wet state or after the mix has hardened. So, this is a general definition of admixtures. Of course, today what we are looking at, we are concerned more with this one, we are concerned today we are concerned more with this one, this particular type wet, which modifies the concrete in wet state, right. So, all right. So, that is what the definition of admixtures are. It can be a single chemical or can be a blend of various chemicals. Usually they are in solutions forms, usually water based, typically 35 to 40% active chemicals, 35 to 40% active chemicals, and the amount added are very small, usually less than 5%, mostly less than 2%, very small quantity, 2% by mass of the cement itself. Very small quantities are added, mostly less than 2% by mass of the cement itself. So, very little quantity we add, but they modify the properties. So, that is the basic definition of admixtures, and we can use some of those admixtures which will actually improve the fresh concrete properties, consistency or workability of the concrete, and that is what we will look into in details today. There are other kind of admixtures, namely let us say accelerators, which will accelerate the strength gain process of concrete, a retarder which slows down the process of hydration. I will just mention this sometime, and several others which are relevant to our discussion. So, some of them I might mention at some point in our discussion today, but mainly our focus would be on water reducing admixtures. A little bit of history is important. This has come much later than the concrete, but today of course, most of the concrete you can't think of concrete without some form of admixtures or other. One variety which we will discuss called plasticizer actually came in 1932. Then there is something called air entraining admixtures, we will also again mention about this today. They came in 1941, and then superplasticizers is a similar variety, some improved variety, they came in 1963, and then this is some variety, this was already there at that point, but today it is in a modern form, it has come, possibly one can call it as a hyperplasticizer, and its development is 1990 to 1999. So, that is the kind of history that is there. Right. Let us see now, discuss in general a little bit about various kind of admixtures. They can be discussed in terms of the mechanism of their actions, because all admixtures do not act in the same manner. All admixtures do not act in the same manner, right. So, let us discuss them in the light of their action. So, first of all, there are certain admixtures which interacts in the process of hydration. they are accelerators and retarders. They are accelerators and retarders. I mentioned accelerator. An accelerator accelerates the strength gain. All right. Calcium chloride is one of them, but we will not discuss much about this. But retarder has something to do with the phase state also. Let us discuss a little bit about this. Retarders. The retarders actually slows down the hydration process. Now, sugar is one of the retarder. Sugar is one of the retarder. Okay. Sugar is one of the retarder. If you add sugar to the concrete, it actually interferes with the hydration process and slows down the hydration process. So, this can be used where you want to delay the setting. This can be used where you want to delay the setting. Well, there are many other, I mean, chemical retarders are there, which may come from even sugar or some sort of sugar, presence of sugar. So, this retarders actually reduces down, slows down the rate of hydration, and therefore, supposing you want to delay the setting process, retarders are used. Typical example would be in a ready mix concrete truck. You can use the retarder so that it does not set while traveling. In addition to agitating, you can use also a retarder. Similar other place where you expect that your compaction time required would be relatively more, the time required when you can, or placing time would be relatively more, you have to long haul or something of that kind, you can use a retarder. So, retarders are one which actually retards the setting process, although they may not necessarily affect the later on strength development characteristics. Okay, so this is one, they actually interfere with the hydration process, interacts with the hydration process and change the hydration process. The second variety is surface acting type. We will look this into more detail, and they generally cause particle dispersion, and that is what we are going to look into, plasticizer and super plasticizers, etc. So, they essentially are adsorbed at the surface of the cement particle or cementitious particle and causes actually dispersion of the particle. And as we have seen earlier, this dispersion of the particles means the distance between the particles are increasing. So, when distance between the particle increases, delta, if you remember from our last lecture, delta function, delta minus 0.6 nu equals to 1.3 delta minus, something like that, minus 1 if you remember. So, if you increase delta, the dispersion of the particle, the viscosity will reduce, and this reduction in viscosity means that it will give some sort of mobility. So, viscosity reducing actually effect, they cause dispersion, which in turn will reduce viscosity of the cement paste system. So, right, these are plasticizer and super plasticizer does that kind of thing. Something which affects the surface tension of water allows bubble formation, so they allow air entrainment. So, this also we will mention today, because this 3 relates to the fresh concrete. So, increased air entrainment is required for some some specific purpose. I will discuss this sometime later on in this lecture itself, but this means that actually you are affecting the surface tension of the water to form bubbles. So, this admixtures actually affect the surface tension of the water to form bubbles, and that is how they form bubbles, and these bubbles in turn helps in workability, but they do much more for freeze thaw against durability. They improve the durability against freeze thaw action. So, that is important, they improve the durability against freeze thaw action. Now, some can increase the viscosity of water. Okay. If you add certain type of hyperplasticizer, over certain dose to increase the mobility, you increase the mobility all right, but this might lead to actually bleeding or separation of the water or segregation of the water from the rest of the material. You have caused such dispersion that and lot of water became free, the water itself might move away, remain go away alone, leaving the rest of the part. So, this is a kind of segregation, that is bleeding. If you want to reduce that bleeding, at the same time you want a lot of dispersion, to reduce this bleeding what you add is called viscosity modifier, and this actually changes the viscosity of the water. So, this affects the rheology of water, viscosity modifier. So, viscosity modifier are essentially used in self compacting concrete, not in ordinary concrete. So, we will not have much discussion on that, but at the moment let us discuss about this. The viscosity modifier actually increases the viscosity of water and therefore reduces the bleeding tendency or segregation tendency of self compacting concrete. Well, our discussion will mainly focus on this. We will also discuss something on this in terms of chemical admixtures, but then of course, we will go to mineral admixtures, right. So, that is the first stage. So, we are focusing our discussion on dispersing admixtures, and as you can see 60% of the consumption of admixtures in the world, actually 60% is the dispersing admixtures. That is, majority of the admixtures are used for plasticizing or improving the workability of concrete. Just to little bit digressing from here, I did not mention about many other admixtures like corrosion inhibitors and several other admixtures are there, because that is not part of the fresh concrete discussion. So, but if we have time, we will discuss them at appropriate time, but here we are only concentrating on to mainly on to dispersing admixtures or whatever modifies the fresh concrete properties, right. So, coming back to this, plasticizer, super plasticizer and hyper plasticizer, all of them are dispersing admixtures. They are all dispersing admixtures. In other words, they cause dispersion of the particle, and we know why they, how do they actually dispersion of the particle, what it would do? It would essentially cause reduction in the viscosity of the cement system. It will cement paste system, and therefore flowability of the cement paste would be improved, and that in turn should improve the flowability or deformability of the whole concrete system, and therefore improves the workability. So, that is the plasticizing effect. So, first variety in this one we call as plasticizer, and this plasticizer is the one that was the earliest developed, plasticizer was the ones which was developed earliest. They can reduce the water by about 5 to 12%. Well, these are also called water reducing agent. In American terminology, generally these are called WRC, water reducing agent, WRC, water reducing agent, WRC is the water reducing agent. So, it can reduce the water 5% to 12%. That means, you can have a reduction of water between 5 to 12%, and you will get the same consistency of the concrete when you use this from about 0.2 to 0.6% as a percentage of cement. So, when you use very small quantity 0.2 to 0.6% of this plasticizer or this chemical admixture as a percentage of cement 0.2 to 0.6, you can reduce the water requirement for the same viscosity or consistency of the cement by 5 to about 12%, because this causes dispersion of the cement. So, therefore, dispersion of the cement which earlier you were getting through the water, well, you can put much less water and can get the same dispersion. That is the idea. So, that is what it is. The dosage are 0.2 to 6% and they ensure dispersion, right. What are these materials? The materials originally they were lignosulfonates, natural polymer from wood after removal of sugar. Why remove sugar? Sugar will otherwise cause retardation. If we do not remove sugar, sugar will cause retardation. So, this we remove because it causes retardation. So, basically it is the wood has got lignin, actually cellulose fiber embedded in lignin. So, it is the lignin material. The paper industry actually when it uses, some of these materials can come from paper industry. So, this lignin is sulfonated. So, it is actually natural polymer from wood, and the sugar is removed, the lignosulfonate is obtained. So, this is the original kind of the very early plasticizers which were there, and today also majority of the plasticizers raw material is this. This is modified, based on this the product is formed, and plasticizers are usually formed. The other could be carboxylate ether, other could be polycarboxylate ether based plasticizer, that was also quite early. Carboxylic acid has got COOH, oxalates this is poly, this should be polycarboxylate ether based plasticizer. So, the acid reacting with alcohol gives you ethers. So, this polycarboxylate based plasticizer, they are the other ones. These ones are used for low to medium slump concrete, and their water reduction is limited to 5 to 12%. water reduction is limited to 5 to 12%. So, they are used for medium to low slump concrete, low to medium slump concrete. As opposed to this, we have something called superplasticizers. Now, these superplasticizers were developed later in 1963 as we mentioned, and they are superplasticizers. So, with reference to plasticizer, they can actually reduce the water much more, as you can see, from 12 to 32%, and eventually their doses are also higher, 0.6 to about 2%, not 0.2%, but this is 6 to about 6 to about 2%. This is not point, it is 6 to 2%, 0.6 to 2% on cement. So, water reduction is from 12% to 30%, and earlier you have seen that was 5 to 12%, this reduces much more. So, superplasticizer requires more dosage, but at the same time reduces the water more. That means, they can disperse the cement particle more. So, you have to add less water for the same dispersion. So, you get similar consistency with much less water. They are synthetic, and there are three main types. Sulfonated polymers, first one is a sulfonated polymers of naphthalene, second one is melamine, naphthalene or melamine, naphthalene formaldehyde condensates or melamine formaldehyde condensates. So, there are the three main types, one is a naphthalene polymers of naphthalene formaldehyde condensates, second one is melamine formaldehyde condensates, and third variety is the polycarboxylic ether type. So, the superplasticizers are based on this naphthalene formaldehyde or melamine formaldehyde condensates and polycarboxylic ether. Right. They actually reduce the water much more, we have seen, and their dosage are also high. Hyperplasticizer is mainly based on polycarboxylic ether type, and they do this action is much higher, which is a recent development and much higher, because all these are basically nothing but long chain polymeric molecules, and they get absorbed at the surface, as we shall look through the mechanism, and causes a kind of charges. Now, if you have surface, if you have chains and then branches also, the polycarboxylic ether types have similar branches, and which further can cause more dispersion. The superplasticizers have simple long chains, but the polycarboxylic type has got branches as well. So, therefore, they can actually cause lot more dispersion, and thereby they can act much more. So, can be much more active than the melamine formaldehyde condensates or naphthalene formaldehyde condensate type, right, and that is what has resulted in hyperplasticizers. Let us see to the mechanism of their action. Water reducing agents or water reducers are or plasticizers and superplasticizers and hyperplasticizers, they are all water reducers in general terms. They are actually surface acting agents, and they get absorbed on the cement and fine particles, that is fly ash, silica fume, etc., and they do give negative charge leading to repulsion of these particles. So, these particles they get absorbed at the top of the surface, and once they are absorbed they make them negatively charged, and thereby since these particles are all getting negatively charged, they are repelled by each other, and therefore, the dispersion is attained in this manner. Earlier, by addition of water you were actually causing dispersion of these particles, but now by addition of less water actually you are able to disperse these particles, because they are negatively charged, A second action is of course, the negative charge also causes development of sheath of oriented water molecules around the particle. This is because we know that water is a polar liquid, the water has got a dipole moment. In H2O, the center of positive charges and the negative charges they do not coincide. So, since they do not coincide, it is a polar liquid, and it can get attached to the negative, oriented around that negative charge formed, and therefore, causes a development of sheath of oriented water molecules, and this results in some of the water being getting released from restraining mechanism when it happens, mechanisms of flocculated system. So, when you do not add the plasticizer, cements are flocculated and they restrain the water, because water is no longer oriented and they sort of, it is not free, it is not easy to move, and some water gets freed because they are now oriented, and because the restraining mechanism of flocculated system is no longer available, it is all dispersed, and this water, which is additional water, is available, this is free for lubrication. So, therefore, it releases the water not by one means, but by more than one means. First of all, negative charges, these are this adsorbed and negative charges causes repulsion. Then sheath of oriented water molecules resulting in free water, and that would actually be available for lubrication. So, this is the mechanism how does this plasticizer and super plasticizer acts. So, the one which are more effective in getting adsorbed to the surface, they act more. So, super plasticizer acts more than the plasticizer, and hyper plasticizer can cause more dispersion, resulting in more effectiveness. Okay, this diagram perhaps would give us the idea how do they act. This diagram will give us the idea how do they act. This was you can see the cement flocks which has got less, the fluidity is relatively less, they are all together the particle. So, when you add dispersing admixtures, this get adsorbed at the cement grains, and the cement particles are now individually separated, because they are not together. Like clay particles which are charged, cement particles are such fine particles. So, they have a tendency to get flocculated, and this dispersing particles, once they get adsorbed at the surface of each of these particles, they get adsorbed at the surface of each of this particle, they cause their dispersion. Not only that, as we have said that the water molecule will get oriented around these particles, form a sheath of oriented water molecule, and thereby releases some of those water for which was available, which was not available earlier, now becomes available for lubrication, and thereby actually reduces the water required for same plasticity, same plastic condition or same consistency. Okay. Right. So, let us follow it up. Let us look into some other effect. As I mentioned that hydroxylated carboxylic type, they are the one actually which can be more effective, they can be more effective, very effective, and when used in large doses can lead to bleeding, especially when you have high workability concrete, in case of basically self compacting concrete, right. And what you do in such case, then you use a viscosity modifier I mentioned earlier, which will thicken the water. It's some sort of thickening agent, water thickening agent, actually some sort of water thickening agent which will thicken the water. Well, this can also be done, I mean, one way to improve the viscosity, or getting the viscosity modifying effect, reduce down the segregation, is to use very fine other cementitious material in self compacting concrete, but that is anyway not our discussion at the moment. So, this can happen, but then you can use a viscosity modifier. Lignosulfonic acid once of course improves the cohesiveness by entraining air. Not all other plasticizers and super plasticizer actually entrains air, but lignosulfonic based, the one based on lignosulfonic acid can improve the cohesiveness of the system as well. A secondary effect, and it is positive in some cases or most of the cases, as we shall see, is that rate of hydration can be increased, particularly with some super plasticizer, because now you have got better dispersion, particles are all separated. So, therefore, the hydration rate will be higher, the hydration takes place from surface. So, hydration rate will be higher, that is what we have seen in case of expanding cluster model when we were looking earlier. So, therefore, hydration rate can be increased, because it will have more uniform structure also, since the particles are separated off, they are dispersed, they are not close together, they are dispersed, there is the distance between them. So, uniform hydration will be possible, product formed will be uniform rather than a clogged system where particles are, the hydration product would have come something like this, but here it will be a more uniform distribution of the hydration product, and it would be surely improving the long term strength, long term strength will be improved significantly. Okay. And this is what is seen in case of high performance concrete, that this happens with use of superplasticizer. Well, some cases low C3A and low alkali content cement have more influence on strength. As far as strength is concerned, low C3A and low alkali cements have better influence on strength. Right. So, let us see how can you use them. First of all, supposing I have a concrete S, I am denoting here for strength, and its strength is equals to A, and let us say workability is B. Now, I want to increase its, let us say, strength, reducing the workability. What will I do? I will reduce down the water cement ratio. So, if I want to reduce down the water cement ratio, I will add cement. So, if I add cement, then what will happen? My strength will increase. As can be seen, the strength will increase. As can be seen, that the strength is now greater, but the workability has remained same, because I have kept the water same. The paste will have little bit less consistency, but generally would not affect, because water, the water cement ratio usually in concrete is relatively high. In normal strength concrete we are talking of, and therefore may not affect the workability significantly. So, it will remain same, although the water, the paste content has increased and slightly drier paste, but the paste itself will be consistent enough, because water cement ratio, we are talking of normal strength concrete, and water cement ratio is sufficiently high to make the cement paste consistent. So, workability will remain same, workability will nearly remain same, by my strength will increase. Okay. Supposing I want to get a second effect, and I did not add any admixture to this. Now, I want to get a second effect, I want to increase the workability as well as maintain the strength same. I want to increase the workability and maintain the strength same. Then what I will do? I will add some water, but I will add cement, so that my workability has increased, but strength has remained same, because I have added water and cement in such a manner that water cement ratio has remained same. So, I have added some water, added some cement, strength is same. Now, this same effects I can get now with plasticizer or superplasticizer. Let us see how. Now, supposing I add water reducing agent, that is plasticizer plus water with this concrete, then I have added water reducing agent plus water reducing agent, but actually this is cement is not necessary. Water reducing agent I have added water reducing agent, but I need not add any cement onto it. Water reducing agent, there is no need for adding water, I just add water reducing agent. I'll get okay. I have added water reducing agent, and then what would it do? If I want to keep my workability same, I will actually reduce my water, it should be minus W, I will reduce some of my water. So, I have added water reducing agent, I will subtract some water. Now, since my W by C has to be same, then I can subtract some cement also. So, in this one actually I will subtract water reducing agent. Just simply if I just add WRA, I will get water can be reduced, keeping, if I keep the cement content same, then my strength will increase. So, I just add water WRA, I reduce my water a little bit, keeping the cement content same. So, do not reduce the cement content, keep the water cement ratio is same. So, water cement ratio itself will reduce. So, just add WRA, reduce a little bit of water, keep the cement same, C is constant, keep cement same. So, W by C will be lower, it will be lower, so strength will increase. So, one way is to add W by RA, reduce water, keep the W by C same, and or W by C will increase, increasing the strength. Second way would be, supposing same effect I am trying to get. So, what I was doing, I was getting 28 days strength higher, workability same by adding cement, but here I did not add cement, instead I added WRA and just reduce the water. So, cement I did not add, and if the cost of this WRA is less, then I will get a saving. So, compared to the added cement, then I will get a saving. So, I can add WRA, reduce the W a little bit, keep the cement same, then I will have my increase in strength, workability will remain same. A second case could be I add WRA minus W minus C, I will maintain the strength same, workability same, because if I add WRA, I can reduce the W, reduce the water to maintain same workability. I can reduce some cement such that W by C is constant in this case, then I will get same strength. So, you see, by adding WRA, I can actually save on some cement for the same strength and same workability. Now, supposing if I am saving in cement, the reduction in cement, cost of the cement is less than, I mean more than the cost of the saving that I am getting in cement by reducing cement is more than the cost of the WRA, then this will be economical. So, I can use it in this manner as well. A third way I can use it is actually by adding WRA and doing nothing. So, if I add WRA, my water content remains same, cement remains same. So, my strength will remain same, but my workability will increase. So, adding WRA ensures that just adding WRA, my strength will remain same, because I am maintaining the water by C is same, constant, water by C is constant, but workability will increase, workability will increase because I have added WRA. So, same thing I can do it in different manners. You see, by adding WRA and subtracting W, by adding WRA and subtracting W, keeping the cement same, my water to cement ratio would be lowered. So, strength increases. So, the same strength increase which I was getting through adding cement, now I can do it by adding water reducing agent and reducing water. Now, this cost of this, if this saving, the cost of this and cost of this I can compare. If this is cheaper, I can follow this route. If I want to maintain the same strength and same workability, I can reduce the water cement ratio, but W by C I keep it constant, simply same, constant, I keep it constant. So, W by C I keep it constant, W by C I keep constant. So, I reduce W, I reduce C as well, but add WRA. Now, the saving that I am getting by reducing the cement, if that is more compared to the cost of the WRA, which is added in very small percentages, then I am getting a benefit using superplasticizer or plasticizer. So, usually there is a benefit of doing that, because this cost should be relatively small. A third case would be simply increase the workability, do not change anything, keep W by C constant, add workability, add WRA, you will increase the workability. So, increasing workability is possible. We have mentioned by increasing water earlier, but if I add WRA, then simply also this is possible. So, this is one way of action. This is the ways of actions of water reducing agent. Well, this diagram will show this same thing again in a little bit more detail. This axis is water content, this axis is flow table spread, which is a measure of workability or consistency of concrete or even paste or mortar or whatever it is. Usually this is for concrete, this particular case is for concrete. So, if you have, as I go on increasing the water without superplasticizer, this is the curve. With superplasticizer, this is the curve. I require much less water, you can see much less water, I need much less water. So, this curve shows the with superplasticizer and without superplasticizer. There is a water reduction, same flow I am getting, flow is constant, same 400 flow, this much of water I need here, and in this case I am needing this much of water. So, there is a significant reduction in water. So, what I do, same thing, same action I said, supposing I go simply along this direction, I will reduce my water, if I keep the cement same, I will increase the strength of the concrete, like I mentioned earlier. If I keep my water same, then it will increase simply the flow, So, if I increase the water same and go upward, just use the WRA, it will increase my flow. So, both actions I can have, I can increase my flow just by adding, I can increase my, I can make strong very high, because I can reduce down water. If I use the cement same, keep the cement same, strength could be increased significantly. So, same action what I mentioned earlier This diagram also shows the water reduction, and we conclude to the same thing, that I can, by using efficiently or economically, I can use water reducing agents or high range water reducing agent. These are called, the water reducing agent and high range water reducing agent, that is plasticizer and super plasticizer. I can utilize them. First of all, if I just add them without changing anything, then my flow will increase. If I add them and reduce the water cement as well, then I will save on some money on cement, because water reducing agent might cost less, keep the strength same, workability same. A third way could be reduce the water, but do not change the cement, then water cement ratio will reduce significantly. For the same workability, strength can be increased. So, that is the advantages of plasticizer, super plasticizer. Right. Now, I was mentioning about the dispersion, strength improvement of the super plasticizer. This diagram shows you that. You see, this shows the super plasticizer dosage, which are about 1, 2%, etc., 3%. And if you look at the compressive strength in MPa of concrete, then this is at 8 hours, 12 hours, 24 hours and 28 days. Now, if you see that early strength, if you use the increase the super plasticizer dosage, early strength increases. So, at 8 hour strength without super plasticizer and with super plasticizer, it is much higher. That is because the dispersion cost by the super plasticizer has actually resulted in improvement in hydration, and this is also seen in 28 day strength as well. So, there is because of the uniform structure is formed, there is a better dispersion, no flocculation of cement, and cement hydrates uniformly throughout the structure of the concrete, throughout the matrix of the concrete or overall in the overall concrete. Therefore, you find that 28 day strength, even 28 day strength, this is improvement, although this is much more pronounced at low strength. At 8 hours, this is much more pronounced without super plasticizer, and with super plasticizer 2 or 3% dosage, the strength difference is pretty high. This difference of course reduces, but still it is there somewhat. So, it gives you an uniform, well dispersed uniform structure of the cement paste in the concrete, and therefore, it shows an improvement in the strength characteristics of the concrete even for 28 day strength as well. So, that is all about plasticizer, super plasticizer and hyperplasticizer, that is water reducing agent, high range water reducing agent, etc., and very high range water reducing agent. Now, the other kind of admixtures which are also affect somewhat the workability are the air entraining admixtures. Well, if you look at air entraining admixtures, their main function is against freezing and thawing. They show good durability performance against freezing and thawing. Air entraining agent essentially improves the surface, changes the surface tension of the water, and thereby creates air bubbles. They are very fine closed air bubble systems distributed throughout the concrete structure. They are uniformly distributed throughout the cement paste or the concrete structure, and when freezing and thawing takes place, initially they are air filled, but in case of freezing, what happens? There is an excess pressure in water filled pores because of the freezing, because ice or occupies more volume. Water when frozen occupies more volume than the liquid water, so it exerts pressure. So, originally air filled space, their surface, their boundaries get ruptured and excess pressure is released, because the water can flow into those pores. Some of the pores will be actually converted into open pores, closed pores due to air entrainment will be converted into open pores in 1 year, next year more and next year more and so on. So, number of freeze thaw cycles they can actually withstand is more compared to non air entrained concrete. Well, that is the main reason why they are added, but anyway that is not part of our discussion at the moment, but they also they improve the workability. They also improve the workability somewhat. So, the air entraining admixtures improve the workability. They would reduce down the strength a little bit by putting air bubbles uniformly dispersed. They actually improves the deformability capability and mobility, and thereby they improve the workability. But durability is the main concern in this kind of structure, this kind of admixtures that was I have mentioned. Strength will be reduced somewhat because the strength would be reduced somewhat because you have introduced new pores into the system. However, you do not mind sacrificing the strength at the cost of the, because you get the improvement in durability at the cost of little bit of strength. So, you do not mind, but a fringe benefit is of course, it improves the workability as well, right. So, that is what is the air and training admixture is about. Okay. Let us look into now the mineral admixtures. Well, we have already mentioned that mineral admixtures are pozzolana, some pozzolana. So, they are added as cementitious material in cement, and we have already mentioned something like fly ash is one of them. I have defined fly ash sometime, but fly ash has got a strong effect as far as workability is concerned. And also other mineral admixtures are ground granulated blast furnace slags, which I have mentioned sometime. Then I have also mentioned about silica fume sometime earlier. Now, these admixtures do have there some effect as far as fresh concrete is concerned. Now, how? So, we will look into one by one. First one is fly ash. Now, fly ash I mentioned the particle sizes varies from 5 to 150 micron, So, they are very fine particles, and these particles to certain extent, unlike to certain extent, although the finer ones will still go in, will show this effect more. If these are my cement particles, these are cement particles, the fly ash particle can go inside. So, that is fly ash particles. So, you will have some sort of pore filling effect would be obtained from fly ash particles. So, these fly ash particles can fill in the pores, So, this is one aspect. Now, if they can fill in the pores, thereby the packing characteristics of the cementitious system itself is improving, and you will require possibly less water to fill in the void space within the cementitious particle. But some water goes in wetting them also, because they should be dispersed, right. But more importantly, these particles are spherical in nature. These particles are spherical in nature. Their shape, the particles, fly ash particles are spherical shape. They are spherical shape. Fly ash particles are spherical shape. They are spherical shape. So, they are spherical particles. I mean, under electron microscope, one could see that fly ash particles are spherical. Some very few particles in them are called cenospheres. Some very small particles in them are called cenospheres, which are actually hollow spheres. Some of them are available in the cement particle, but by and large fly ash particles are spherical in nature. Of course, one must satisfy the requirement or the specifications, appropriate specification, and should have definitely less loss on ignition, because loss on ignition corresponds to presence of carbon, loss of ignition, presence of carbon. So, if you have high loss on ignition, it means that you have sufficient, if you have high carbon content, which will actually these are not spherical particles, they are actually flaky sort of or flat particle, which will absorb a lot of water, and the water demand actually will increase water demand actually increases with this sort of particles. So, carbon content should be low in case of fly ash. So, if your fly ash is good, that means it is fine particles, very relatively fine, it can go into the pores, and it has got spherical particles sufficient. This spherical particles tends to give what is called ball bearing action. This spherical, if it is spherical in nature, other particles can roll over it, packs better, gives a better packing, and other particles can roll over it, and this results in reduction of water. So, this causes reduction in water demand. In fact, it has been seen that fly ash significantly reduces the water demand for same flow. So, for the same flow, water demand is reduced when you add fly ash particles. Right. So, two issues: one, main thing it does is it gives you a pore filling effect, and also it gives you also the fly ash also gives you pore filling effect, and also gives you through spherical particles gives you ball bearing action, and therefore, there is a reduction in the water demand of the concrete when you add fly ash. Most of the code recognizes this, some values I will show you. GGBFS, of course, they are not. GGBFS is not known to be so much spherical in nature, but they are these two are also very fine. So, they can improve the cohesiveness of the concrete in general. One thing here one must understand, coming back to the fly ash, that fly ash reduces the water, all right, but it depends, like it improves, it gives you a cohesive mixture, and this will also give you a cohesive mixture, but you may not get the same slump, although cohesion or consistency may be same for the concrete, even though you may have a lower slump in this case, a little bit lower, usually 25 millimeter lower slump is tolerated when you add fly ash to the concrete. But anyway, we will come back to this when we look into the table of water reduction. GGBFS on the other hand is not spherical in nature. So, this ball bearing action that you get in case of fly ash is perhaps not available, but it can still make it cohesive. Silica fume, this is very fine, and if you remember, this was from 1 to 5 micron size. This is usually the mean size will range from 1 to 5 micron. Deflocculated one has to be there, although larger size you can have. If you have larger size, then there is a problem, but if you have fine size, usually of this sizes, this has got very large surface area, but very large surface area. So, the water requirement, this may not reduce itself, but this material is seldom used without superplasticizers. So, silica fume is used together with the superplasticizer, and usually for very high strength or very high strength concrete system. Using fly ash, since you can reduce water, using this one can reduce water. So, water reduction is possible, and there is a gain in long term strength is also possible, long term strain gain, long term strength. So, you can get somewhat high strength concrete is possible, up to certain level, but very high strength concrete or high strength concrete on the higher side, 100 MPa concrete, 100 MPa concretes are obtained through this, and this is usually with low water cement ratio. Water cement ratio is usually low, and you definitely use a superplasticizer. So, when you are using superplasticizer and silica fume together, the dosage of superplasticizer required is high, because whenever you are using plasticizer or superplasticizer with these materials, superplasticizer or plasticizer with these materials, then superplasticizer or plasticizer with this material, then they cause dispersion of these materials as well. Silica fume being very fine, hence it has got large surface area, usual water requirement is more, but we do not use them alone without superplasticizers, and when you use superplasticizer doses required are more, but then it forms very uniformly dispersed concrete system, very highly dispersed concrete, well dispersed concrete system. That means, you will have cement particles like this, you will have cement particles like this, and which are themselves would get dispersed in some manner by the plasticizer, and the silica fume particles will actually be forming, it will be actually be within the interstitial space between them. So, you have a actually well dispersed uniform system when you use both silica fume and superplasticizer together, resulting in high strength concrete. So, for very high strength concrete over 100 MPa concrete, silica fume plus superplasticizer is the actually material. So, the silica fume as such do not have sort of influence strongly. It doesn't, it is not an water reducing agent, unlike fly ash. Fly ash has got some sort of water reducing capability also, it does not have so much, but it is used together in very high strength concrete and usually in low water cement ratio concrete with superplasticizer, and there this dispersion it consumes more dosage of superplasticizer, but disperse also more, and therefore can give you uniform concrete. Right. Now, water content reduction is some example of water content reduction due to fly ashes. Water content reduction due to fly ashes. Supposing like this comes from the Department of Environment British practice, the mixed design method. So, in this mixed design method it gives you a mixed design procedure involving fly ash also. Now, it gives you a table, part of the table is actually reproduced here, where it shows you supposing the percentage of the cement percentage of fly ash Fa in cementitious. Cementitious means C plus F, where C stands for the cement, F stands for the fly ash. So, F divided by C plus F into 100, that is the percentage in cementitious. If this is 10%, and if your slump is 0 to 10, then this would, you can reduce the water content in the concrete, you can reduce by 5 kg per meter cube. This is in kg per meter cube, 5 kg per meter cube. That means, originally if you have something like 200 kg per meter cube, now you can make it as 195 kg per meter cube. Slump from 10 to 30 mm also, slump from 10 to 30 mm also you can have 5 kg reduction, whereas there are in between others 30 to 60 and which the part of the table that is not shown here. Here also you can have, when it is 60 to 180, the reduction possible is 10 kg per meter cube. So, at higher slump the water reduction is higher, the slump water reduction is higher for the same fly ash content, and as you go on increasing the fly ash content, you can see the water reduction increases, because more the fly ash, more it can actually allow for the ball bearing action and pore filling effect. Okay. Similarly, this again, as you go along this direction, there is an increase. So, you can significantly reduce the water demand by adding fly ash, and this is utilized in the mixed design. So, add fly ash, you can reduce down the water, and therefore, if you want to get the same strength, you can reduce down the cement also. Of course, this is not so simple, this is slightly more modified, because in case of fly ash, the strength is a function of C plus Kf, which we will discuss sometime later on, unlike W by C alone. So, therefore, but you can reduce down the water to some extent, and hence cement consumption also can increase, and you have to redesign the mix completely to get the full beneficial effect. So, fly ash can reduce the water significantly, right, and give you a plasticizing effect, right. But few things must be remembered here. Okay, this we know, the strength increase, we have already seen this. Strength increment with fly ash, 28 days strength can be same and long term strength is beneficial, but what we have seen today is, as far as the workability is concerned, fly ash reduces the water demand. But one thing must be remembered, as I mentioned earlier, that although fly ash reduces the water demand, if you are doing slump, you will find that it might show those otherwise other consistency measure, it might show same, effort required to compact it might still be same, but it might show a somewhat lesser slump, because the pore filling, the pores are also filled by in the cement system is also filled somewhat by fly ash, and it is more cohesive in nature, does not show so much of relatively same amount of slump as without fly ash concrete. So, as 25 millimeter reduction in slump is allowed. So, for example, if a concrete without slump is without fly ash is showing 100 mm slump, a concrete with slump with fly ash, if it shows even 75 mm slump, they might be treated nearly same consistency because of the cohesiveness that the fly ash allows, right. So, by using mineral admixtures we can reduce down we can improve by using the mineral admixtures we can improve the workability. In other words, we can have reduced water demand, and we have also seen that by adding water reducing agent we can have significant reduction in water demand. Air entraining admixtures, their purpose is of course to provide better durability against freeze thaw action, but they do reduce down the water demand somewhat. Importantly, when you both of them you use together, the water reducing agent and the mineral admixtures, you can have lot more choice available. Simple water reducing agent, we have seen the choices those are available is limited. Either I can have same strength, same workability with lesser cost, because water reducing, by using a water reducing agent I can reduce down possibly cement, and thereby it can be economic. Sometimes it can be economic to use water reducing agent, or I can increase the strength by reducing the water, keeping the cement same, or I can increase simply the workability. So, these three options were available when I was using only water reducing agent, but if I use water reducing agent and silica fume, or I mean fly ash together, it can open up lot more possibilities. I mean so reduction in the cement can be still higher by using fly ash, because it further gives you a reduction in water and also can show you improvement in the long term strength. So, a combination of this type of admixtures can give you large amount of benefit. Something more in our summary is also we discussed a little bit about viscosity modifier, which actually thickens the water or sort of improves the viscosity and reduces down the segregation. And also you discussed about something about the retarders, which would actually slow down the process of hydration and thereby allow the placement of the concrete over a longer period of time. So, these are the kind of advantages you get in case of plasticizers, super plasticizer, hyperplasticizer and other admixtures, mineral admixtures. But one point which I have not mentioned and I would like to mention at the end is that all plasticizers and super plasticizers are not compatible with all system. While you might find that it reduces the water, one might actually delay the setting process significantly. There can be side effects from super plasticizers or plasticizers, especially when added in excessive dose. So, dosage should be within the limit specified by the manufacturer, and their compatibility should be tested, that they do not cause any reduction in the any elongation in the setting time, nor do they cause any kind of segregation in terms of bleeding, etc., or any other secondary side effects that is there in the concrete. So, this is most important. One must test for the compatibility of the plasticizer whenever you are using a plasticizer or super plasticizer which is compatible with one cement may not be exactly compatible with another cement. So, while using them, and this has to be done by trial and error, their use in mixed design is also by trial and error. And I think with this we can say conclude the discussion on the admixtures in concrete, and thank you for hearing. Next class we shall discuss about segregation and bleeding in fresh concrete. Thank you.